This is section 9.3, part D, Inference for Means, Paired Data. Comparative studies are more convincing than single sample investigations. For that reason, one sample inference is less common than comparative inference. Study designs that involve making two observations on the same individual or one observation on each of two similar individuals results in paired data. We saw an example of paired data in the job satisfaction study in section 9.1. In this match-paired experiment, each worker's satisfaction was recorded twice. First, after self-paced assembly work, and then again after machine-paced assembly work. When paired data result from measuring the same quantitative variable twice, as in the job satisfaction study, we can make comparisons by analyzing the difference in each pair. If the conditions for inference are met, we can use one sample T procedures to perform inference about the mean difference mu sub D. These methods are sometimes called paired T procedures. So let's take a look at an example. Researchers designed an experiment to study the effects of caffeine withdrawal. They recruited 11 volunteers who were diagnosed as being caffeine dependent to serve as subjects. Each subject was barred from coffee, cola, and other substances with caffeine for the duration of the experiment. During one 2-day period, subjects took capsules containing their normal caffeine intake. During another 2-day period, they took placebo capsules. The order in which the subjects took caffeine and the placebos was randomized. At the end of each 2-day period, a test for depression was given to all 11 subjects. Researchers wanted to know whether being deprived of caffeine would lead to an increase in depression. So the table below contains data on the subject's scores on a depression test. Higher scores show more symptoms of depression. So why did the researchers randomly assign the order in which subjects received a placebo caffeine? Researchers want to be able to conclude that any statistical significant change in depression scores is due to the treatment themselves and not some lurking variable. One such lurking variable is the order of the treatment. Maybe if caffeine was given first to all subjects, it might lead to less depression during the placebo treatment than if the placebo was given first. Random assignment of the caffeine and placebo to the two time periods in the experiment should help ensure that no other variable is systematically affecting subjects' responses. Carry out a test to investigate the researcher's question, whether being deprived of caffeine would lead to an increase in depression. So this is going to be a 4-step problem. Remember, when we do a 4-step problem, you start with state. In the state, you are going to give your two hypotheses, you're going to define the parameter, and you are going to give your significance level. So for the state, we can say, if caffeine deprivation has no effect on depression, then we would expect the actual mean difference in depression scores to be 0. We therefore want to test the hypothesis that our null hypothesis is that the mean of the differences is 0, and the alternative, this should be an A, for the alternative hypothesis is that the mean of the differences is greater than 0, where mu sub D is the true mean difference of placebo minus caffeine in depression scores. Since no significance level is given, we will use alpha equals 0.05. Next is the plan. In the plan, you need to tell what method you're going to use, and you need to check your conditions. So for this one, we will use a paired T test to find the mean of the difference. So the first condition we need to check is random. Researchers randomly assign the treatment order, whether they take placebo first or caffeine, to the subjects. So the people doing the activities were not randomly selected because this is an experiment. As long as the treatments are randomly selected, we still have met that random condition. Next is normal. Because we are looking at means, if the sample size is at least 30, we can use our normal conditions. Otherwise, we will have to graph the data. And so since this is only 11, we would need to graph this data and we would look at it. If you look at the box plot, there is some skewness, but it is not very like a huge amount of skewness, and there are no outliers. There's no strong skewness. The probability plot is semi-linear, so we can go ahead and do the normal procedures. We also need to check independence. We are not sampling, so it's actually not necessary to check that 10% condition. We can assume that the change in depression scores for individual subjects are independent. So we're assuming that how one person scores is not going to affect how a different person scores. Next is going to be the do. This is where we do our caffeine. So you do need to input this data into your calculator. You can either find the difference by hand and then input it into the list, or you can have the list do the work for you. So if you would like, you can input your caffeine data into list 1, your placebo data into list 2, and we're finding the difference to be placebo minus caffeine. So in list 3, you can create it to be list 2 minus list 1, and so we will have the differences in list 3. You could then do the one variable statistics in list 3, or again, you could have done the subtraction by hand and put it all in list 1 and then just do the one variable statistics for list 1. But from this data, we get the mean difference is 7.364 with a standard deviation of 6.918. Now this is a mean, and we do not know the population standard deviation, so this is a t-test. So this is why we're doing a paired t-test. So when you are doing the t-test, to find our test statistic, remember it's x bar minus mu sub d all over standard deviation divided by the square root of n, which in this case will give us 3.53. From here, we can look at table B, or you can do this on your calculator. If we use table B, we need to find our degrees of freedom. We had 11 subjects, so 11 minus 1 gives us a degrees of freedom of 10. So if you go to degrees of freedom of 10 and go across the row, you're looking to see where 3.53 would fall, and it's going to fall between 3.169 and 3.581, and that's going to give us the p-values of 0.0025 and 0.005. So we do know our p-value will fall between those two values. Now we can write our conclusion. So with a p-value between 0.0025 and 0.005, this is going to be less than our chosen alpha level of 0.05. We can reject the null hypothesis. We can therefore conclude that depriving these caffeine-dependent subjects of caffeine causes an average increase in the depression scores. So a few follow-up comments about this example are in order. First of all, although the differences in depression, these scores for the 11 subjects are independent, the 2 depression scores for each subject are not independent. When you are working with paired data, the independent condition refers to the differences. Next, the subjects in these experiments were not chosen at random from the population of caffeine-dependent individuals. As a result, we cannot generalize our findings to all caffeine-dependent individuals, only the individuals like the ones who took part in this experiment. Because researchers randomly assign the treatment, however, they can make an inference about cause and effect for just these people in the study. Also, you need to remember a confidence interval gives more information about a significance test. Because this is one-sided test, and our alpha level is 0.05, the corresponding interval would be a 90% confidence interval. And our 90% confidence interval would give us a score or an interval of 3.584 to 11.144, where the T-star that we found was found in table B using our degrees of freedom equal to 10 and a 90% confidence interval. And remember, we are 90% confident that the interval from 3.584 to 11.144 captures the true mean change in depression scores of the mean differences. That is, the data gives convincing evidence that depriving individuals, like the ones in this experiment, of caffeine results in an average increase of between 3.5 and 11 points in depression test scores. Now we do have some cautions. Remember the wise saying, statistical significance is not the same thing as practical importance. Also, when planning a study, verify that the test you plan to use has a high probability or power of detecting a difference of the size you hope to find.